So this is the critical speed experiment. So here we'll determine the critical speeds, also what is the natural frequencies of the shafts. So before that, as we know about the observation, observation length of the shaft L is 100 centimeter, E which is given 2.06 10 to 6, G is 981 centimeter per second square. Diameter of shaft will take the diameter as 0.5 here. So we have different diameters also, we can test it on different diameters also. But here right now we have set it to 0.5 centimeter. Next, moment of inertia of the shaft I is 25.8 10 to minus 4 ms4. This is the already given values. Weight of the shaft is per centimeter is per meter is 0.1 for 10 to minus 2. And these are the end conditions. So the end conditions support fixed and fixed. So support means we will use the different bearings. So these bearings are the fixed support, they don't move. These are called the fixed bearings. They are called the fixed bearings. And support bearings are these which are installed. So they have they move, they have slight translatory motion. So both are at supported bearings, means they have some slight movement, but these are the fixed bearings, they don't move. So this causes the fixed bearings. So right now we have attached a support bearing. So support bearing. So we have first mode of, we have constant K. This is the stiffness value, constant K for the first mode of rotation 1.57 and second mode of rotation that is 6.28 for the first frequency, natural frequency, second natural frequency. So we will use this in the calculation time. Now we will just run the machine and we will find the first and second mode of vibration. So for the first mode of vibration, we will see a single I, and for second mode of vibration we will see a 2I. So now let us start the machine. So on the thermostat and move it very slowly till it rotates. Rotate very slowly. As you can see, the first I at this condition, note down the RPM. So 1415. So 1415. So this is the experimental RPM, that is 1400. So for the diameter of shaft 0.5 and condition support mode 1, that is the stiffness is 1.57 as we know. So this is the experimental RPM 1400. This will calculate later. Now also by experimental RPM we will calculate the second mode of vibration. So for 0.5 support 2 6.28, and now we will calculate this. Just by increasing the speed we will calculate the we will see the second mode of vibration. For now we will see a 2I. So instead of 1 we will see a 2I. So just we will start the machine now. So this is 1I. See, there are 2 eyes. Here and here. Now, so the RPM. 2741. Now switch off the machine. So the experimental RPM is 2741. This is the experimental RPM. Now we'll calculate the theoretical RPM and let's check whether it matches with the experimental RPM. So we have formula to calculate the theoretical RPM. We have the formula F equals to K into root of EIG WL raised to 4. So substitute the values of first reading. So for the first reading, to find theoretical RPM for the first reading, first mode of vibration. So K is 1.57. K is 1.57 root of E. This is E I G upon W L raised to 4. L is 100 centimeters raised to 4. We get 9.27. So 9.27 the theoretical RPM into. So this is RPS. To find the RPM, so multiply with 60. So we get 556 RPM. So this is the RPM, theoretical RPM after calculating with the formula. Similarly, calculate the second theoretical RPM for second mode of vibration. For second mode of vibration, K will be 6.28. The solve will be same. E I G W L S to 4. This will be same. Just the K will change. So we'll get into 60. We'll get the RPM as 225 RPM. So this almost matches. Since because of the damping, the first value may not match with the theoretical RPM because of damping effect, but at higher speeds the damping gets neglected and theoretical RPM and experimental RPM are almost the same. So this is the experiment on the critical speeds. Lastly, write the result of theoretical RPM and experimental RPM.